In our earlier lessons, we stated that every channel was plagued by noise. In today's discussion, we're going to explore the metric of signal-to-noise ratio, which will give us some understanding of what that means. And it allows us to take the next step where we can talk about the capacity of a channel. To get us started, let's go to GNU Radio and look at noise. Let's listen and see if we can find the signal amongst the noise. Maybe you could hear it, but I certainly couldn't. Let's shift to a waterfall display and see what we can see. Right here at 1 kilohertz, it looks like there's a tone that's being turned on and off. But it's very difficult to see because there is so much noise in this channel. It's hard to see the signal through the noise. However, if we go back into our flow graph and we add a nice narrow filter, maybe we can hear it. Let's call this our first lesson in signal-to-noise ratio. It definitely has something to do with the bandwidth. When the spectrum was completely filled with noise, as we saw earlier, it was difficult to hear that signal. Now that we have a very narrow filter that only allows the signal through, it's much easier to hear. We're talking about noise. In the time domain, suppose we had a sinusoid. Noise is just garbage that rides on top of that sinusoid. Here's something you might find interesting. If we were to look at a square wave or a digital signal, it still might have the same amount of noise riding on top of it, but it's relatively easy to recover the original square wave. We might establish some threshold here and here, and we simply say that if on average we are higher than that threshold, that must be a 1, and if we are lower than this threshold, it must be a 0, which means we can recover digital signals easier than we can recover analog. But it's even better than that in the digital world, because we have things like error correction codes that will allow us to recover bit errors. Signal-to-noise ratio, SNR, is a ratio, as the name implies. So we could express that SNR is the power of the signal over the power of the noise. And since it is a ratio, I think you know exactly where we're headed next. SNR is equal to 10 log of the power of the signal over the power of the noise. As far as the quizzes and exams are concerned, you can expect the same type of problems as you had when we're dealing with gain. For example, you may be given an SNR in dB. We should add dB here. And you might be told the power of the signal, find the power of the noise, or some combination of that 3. Anyway, there are 3 variables. You'll be given 2 and asked to find the third. Do keep in mind there is a difference between dB and this here, which we're going to call linear. Noise has multiple sources. There are what we call external noises, including man-made, motors, generators, high power switching. When you think about it, that's most of our shipboard systems. There's atmospheric noise, which includes lightning and the auroras. The final external source is galactic, which are extraterrestrial cosmic noise. By the way, when we're talking about external, we mean things out here that are external to the receiver, not to be confused with internal noise. We could say that external noises are things that live in or affect the channel, whereas the internal noise sources are things that are inside the receiver, such as resistors and semiconductors. As far as internal noise is concerned, we have thermal noise, which is the thermal agitation of atoms, which give rise to spontaneous fluctuations of voltage and current. Semiconductors are a source of noise. Of course, some semiconductors are worse than others. For example, if you were to look up a noise generator, you would find a circuit that looks something like this. A power source, a Zener diode, that's what this one here is, and a resistor. That's it. This voltage out right here is going to be very noisy. Add an amplifier or two, and you end up with the sound that we heard at the beginning of this presentation. There's another internal noise known as intermodulation distortion. This is caused by any nonlinear devices in the signal path. That word nonlinear should mean something to you, because basically anything that's nonlinear is going to act as a mixer. And a mixer will give us sums and deltas. One of the tests we can do for intermodulation distortion is the two-tone test. If we follow the ARRL, we might inject a 700 Hz and a 1900 Hz signal. We'll call this F1 and we'll call this F2. If these tones go through a nonlinear device, we can end up with harmonics, including the second, the third, and the fourth for F1, and for F2, 3800 and 5700. But it's worse than that. If that intermodulation distortion is really bad, these harmonics can interact with each other and with the original tones, giving us summations of F1 plus F2, so that's about 2600, a 2F1 plus F2 at 3300, and a 3F1 plus F2 at 4000. And then there's the differences. So an F1 minus an F2 at negative 1200, a 2F1 minus F2 at negative 500, and a 3F1 minus an F2 at 200. Anyway, I think you get the idea. If there are non-linearities and we inject two tones, there will be tones where there shouldn't be. So that's a challenge to the engineer, is to design systems that are linear. While we're here, let's go back and look at this thermal noise. Specifically, let's look at the noise associated with a resistor. We have an equation. So the RMS voltage is equal to the root of 4 by K T B R, where K is Boltzmann's constant of 1.38 by 10 to the negative 23rd joules per Kelvin. T is the temperature in Kelvin. B is the bandwidth. And finally, R is the resistance. You may want to add this to your note card. The temperature in degrees Kelvin is the Celsius temperature plus 273. And the temperature in Celsius is 5/9 by the temperature in Fahrenheit minus 32. Let's go ahead and work an example using this equation. Start with a 1 mega ohm resistor. We'll assume room temperature as 25 degrees Celsius. That's 77 degrees Fahrenheit. Finally, we'll assume a bandwidth of 5 megahertz. Our opening move is to convert that to Kelvin. So that's 25. Our room temperature plus 273 is about 298 Kelvin. The voltage is 4 by Boltzmann's constant by our temperature. Be careful here. This is Kelvin, not to be confused with kilo. Bandwidth is 5 megahertz. And our resistance is 1 million ohms. The resulting RMS voltage is approximately 290 microvolts, which certainly doesn't sound like a lot, but if that was on the front end of the receiver, I don't think you would hear anything but noise. I'll leave it to you to run this problem again with a more appropriate resistor, such as 50 ohms. That'll certainly help, but it still might not be enough. We can improve things by lowering the temperature using cryogenic methods, with temperatures in Celsius down to about negative 200 degrees. Do remember to convert that to kelvins. The Kelvin temperature is negative 200 plus 273, giving us a temperature of 73 Kelvin. Let's put both of those values back into our original equation and see how well we've improved the noise. This goes to 73. We'll keep the bandwidth the same, but we'll lower the resistor to 50. That yields a very good improvement, as this is now down to about 1 microvolt. Before we finish, I would like to point out two more things about noise, specifically noise in amplifiers. This amplifier has a signal going into it. That signal could be described as SNR going in. It also has a signal leaving. That signal could be described as the SNR out. Likewise, this amplifier might have a power in and a power out. If the amplifier is working, we know that the output power will be greater than the input power. But what about the signal-to-noise ratio? Well, there was a certain amount of signal and a certain amount of noise that went into the amplifier. There is an amplification of both the signal and the noise on the output of the amplifier, but you have to remember that there are gremlins inside the amplifier that will add more noise. So the signal-to-noise ratio on the output of the amplifier will always be worse than the signal-to-noise ratio at the input. We can write that as SNR out will be less than the signal-to-noise ratio on the input. Stated another way, all amplifiers add noise. Keep in mind that signal-to-noise ratio is a ratio. On the input to this amplifier, we had the signal going in and we had the noise going in. It's a division, it's a ratio. On the output, we had signal out over noise out. Because it's an amplifier, we could write signal out as a constant, which is the gain of the amplifier. In fact, maybe we can write that as A. Signal in, right, because we've amplified signal in by the gain of the amplifier, over that same gain of the amplifier by the noise in, plus the noise of the amplifier. With that added noise in the denominator, the total signal-to-noise ratio drops, which is where this comes from. Our signal-to-noise ratio on the output of an amplifier will be less than the signal-to-noise ratio that went into the amplifier, even though the output power on the amplifier is greater than the input power. So those are two related thoughts, but they mean different things. While we're talking about amplifiers, what happens if you have a cascade of amplifiers? I think you'll agree that each amplifier amplifies the noise from the previous stage, which means the signal-to-noise ratio generally degrades as we move through each amplifier. Because of that, it's very important that we get things right in the first stages. In fact, we could say that the chain is dominated by the first amplifier. That is a fact applicable to everything from your home hi-fi, especially if you're still using vinyl. That first stage is critical before you send the signal to the power amplifier. This same consideration for the first amplifier is also applicable to deep space networks, dealing with the large satellite dishes, where we might find a low noise amplifier at the focal point of the dish. Which may be cryogenically cooled for the best signal-to-noise ratio.